Now friends, let us see a new topic which is called inverse of a square matrix. Okay, let's see. Inverse or reciprocal of a square matrix. What do you mean by this? The definition here is, if for a non-singular matrix A of order n, there exists another non-singular matrix B of order n such that AB equals to BA equals to identity matrix of order n, then B is called the inverse of A. It is denoted by A inverse, A power minus 1, A minus 1. Okay, this is the inverse denotion. Now, here B equals to A inverse. See, what does this definition exactly mean? Listen friends, suppose I am having two matrices A, B, both are non-singular. Mentioned both are non-singular. What do you mean by non-singular matrix? Definitely, determinant is not equals to 0. Singular matrix in the sense, determinant is equal to 0, right? So now, if at all this condition is satisfied for a non-singular matrices, if A is a non-singular, B is a non-singular, AB equals to BA, that means which is matrix multiplication is commutative here, right? And which is also equal to identity matrix. Okay, then only B is called the A inverse or A is B inverse. We can write this as if AB equals to I. If AB equals to identity matrix, then A equal to B inverse or B equal to A inverse. Okay, remember this. Anything is possible. Now, it is denoted by A power minus 1 or B power minus 1, right? Now, B is A inverse. Look at the properties of inverse of a matrix. There is already mentioned reciprocal. Reciprocal in the sense power minus 1, right? 1 by A is also nothing but A power minus 1. Now, inverse is also called as reciprocal. See friends. First property, A into A inverse equals to A inverse into A equals to identity matrix. What do you mean by this? If at all a matrix A is multiplied with its inverse, it results to identity matrix. Wherever might be the position, it might be no problem. Whether it is in the prefactor or in the post factor, no problem. It results to an identity matrix. Okay, next one. A inverse is nothing but adjoint A by determinant A. This is the important relation between the adjoint and the inverse of a matrix. Okay, A inverse is nothing but adjoint A divided by determinant A. Now, if at all, if this determinant becomes 0, then A inverse becomes undefined. So, remember, whenever the parameter or a quantity or a number in the denominator becomes 0, then the entire division will become undefined, right? So, if det A becomes 0, A inverse does not exist. If it is 0, you cannot tell the A inverse. Yes or no? So, det A is 0 is nothing but singular matrix, right? So, for every singular matrix, A inverse does not equals to 0. Remember this. That's why he strictly mentioned that non-singular matrices, only for a non-singular matrix only, we calculate the inverse of the matrix. Fine? Now, next see the other property. If A is a 2 by 2 matrix, which is A, B, C, D, it is a 2 by 2 matrix, how can we find the A inverse? See, for a 3 by 3 matrix, we can calculate the adjoint. Previously I have told the shortcut for the adjoint, right? Use that shortcut matrix and divide the denominator with every corresponding element, then you will get the A inverse. We will do the problems, until then hold on. But for 2 by 2 matrix A, B, C, D, 40 is the A inverse, 1 by AD minus BC into D minus B minus C A. Remember this formula. I hope you all know this formula very well, right? Next, if the inverse of the square matrix exists, then the matrix is called invertible matrix. That means for every non-singular matrix, definitely A inverse exists, right? Only for singular matrix itself, that is det equal to 0, A inverse does not exist. Here, if a matrix is inverse is possible for any matrix, then it is nothing but a non-singular matrix, right? Which means every non-singular matrix is an invertible matrix, because we can define A inverse for every non-singular matrix, right? Now let us see the important properties of inverse of the matrix. Okay, see, the first property is AB whole inverse is equals to B inverse A inverse. This is called reversal law. Okay, next one, ABCD whole inverse is nothing but D inverse, C inverse, B inverse, A inverse. Whatever might be the length, how many type of matrices it might be, every matrix is a non-singular matrix. So if it is go on to any number of matrices, from the right to left, you need to put the input, you need to put the inverse of the matrix. Fine. as we see in the transpose, same process applicable here, right? Second one, A transpose whole inverse is equal to A inverse whole transpose. We can interchange. Next, A theta whole inverse equal to A inverse whole theta, right? Next, inverse of an identity matrix is always an identity matrix. Fine. This is the second property. Look at the third one. If A is non-singular and symmetric, then A inverse is also symmetric. First friends, A is a non-singular. That means it is invertible. Okay. If at all that matrix is symmetric, A inverse will also be symmetric. Fine. Next. Fourth one, if AB equals to BA for two non-singular matrices, both are non-singular he has mentioned, then A inverse B inverse equals to B inverse A inverse. Okay, we can apply the inverse if both are equal, right? Next, if AB equals to AC, it implies B equals to C. This here A is get cancelled. It is called left cancellation law, and here it is right cancellation law. Then B equal to C, right? These are two laws. Next one, sixth one. This is a very important property, friends. Basing on this property, he has framed a beautiful gate question. We will see it. See, if A and B are non-zero square matrices, non-zero square matrix in the sense, at least one element will be a non-zero element, right? Not a null matrix. Fine. Then AB will become null matrix. The product of two non-zero matrices will become a null matrix. If and only if A and B are singular. That means if determinant of A is 0 and determinant of B is 0, then only the product will be null matrix possible, right? The null matrix is possible because of the product of two matrices if and only if both of the matrices are singular matrices, then only null matrix possible. If at all, if any one of these two matrices product, if any one of the matrix is a non-singular, then zero matrix will come, but other should be definitely a zero matrix. In the sense, suppose if AB equals to a null matrix, friends. Suppose this is non-singular. If both are singular, definitely we will get a null matrix. Suppose if it is a non-singular matrix in which that is not equal to 0, then B should be definitely a zero matrix. Then only the product will be 0. Right? If both are singular, the product will be a null matrix for sure. Definitely. Not always. If it is a null matrix product means both the matrices are singular. Here, if definitely it is 0 only if and only if it is 0 matrix if it is a non-singular matrix. Fine, remember this property. We will do a few problems on this. Very important. Next one. If A is idempotent matrix, what is idempotent matrix, friends? We already discussed A square equals to A, right? If A is an idempotent matrix, then A is singular except In. See, identity matrix is also an idempotent matrix, right? If A is idempotent, A is singular. That means except for identity matrix, every determinant of an idempotent matrix is 0. The determinant of idempotent matrix is 0 except for identity matrix. Fine. This is a very important property. Okay. Now, if A is an orthogonal matrix, then A inverse and A transpose are also orthogonal. We already discussed it. If A is orthogonal, A transpose is orthogonal. Now we are saying that A inverse is also orthogonal. Fine. Next, Ka whole inverse equals to 1 by K into A inverse. K is a constant here or a scalar, right? 5A whole inverse is nothing but 1 by 5 A inverse. Okay, now diagonal of ABC whole inverse equal to diagonal 1 by A, 1 by B, 1 by C. In the sense, only the diagonal matrix in the sense, non-diagonal elements are 0 and all the diagonal elements will only presence, right? If we apply inverse to it directly, then 1 by A, 1 by B, 1 by A, 1 by B, 1 by C. The inverse, the reciprocal of the values will come in the principal diagonal elements and the remaining all are zeros, right? Now, so these are the properties of inverse of the matrix, friends. Now, these are very important. We have to apply these properties in any sort of gate question. It has come from the inverse of the matrix. Now I will be showing you how to calculate exactly the inverse of the matrix. Okay. Now, let us see how to find the inverse of a square matrix, right? See, friends. First of all, check whether this matrix is singular or non-singular. If it is singular matrix, then A inverse does not exist. Inverse of this matrix does not exist. If at all it is a non-singular where that is not equal to 0, then only inverse is possible, right? We already know that A inverse is equal to adjoint A divided by determinant A. So find determinant A first. So how to calculate the determinant, friends? I have already told the shortcut to find the determinant. 1, 3, 4, right? So yes. Now how to calculate it? So first take this diagonal. 4 4s are 16, 1 16 plus later these two and this element. 3 3s are 9 into 1 9 plus next these two and this element. So 3 1s are 3 3s 9. Yes or no? Now minus. So these are finished. Now calculate for this row. 4 3s 12 plus these two elements into this element. 3 4s 12 plus these two into this element. 3 3s are 9. Right now. So 9 plus 9 is 18. 18 plus 16 is 34. Minus 24 plus 9 is 33. Yeah, we got the determinant 1, which is not equals to 0. Hence, it is an invertible matrix and it's a non-singular matrix. Now we can find the inverse of the matrix, right? See. Okay, fine. Now the determinant is equals to 1. So now we have to calculate the adjoint of the matrix. And I have already told you the shortcut for adjoint also, right? So how to find the adjoint of the matrix? First 1 3 3 1 4 3 1 3 4, right? First extend the first two columns there. 1 1 1 3 4 3. Now extend the first two rows. 1 3 3 1 3 1 4 3 1 4, right? Look at the board, friends. See, first we have to eliminate first column and first row, right? Now how to write the matrix? When we are going vertically, we have to apply those minus horizontally, right? So 4 4s are 16. 16 minus 9. What is the value of 16 minus 9? It's a 7. Right? Next, 3 3 is 9, 4 3 is 12. 9 minus 12 is minus 3. Next, 3 3 is 9, 4 3 is 12. Once again minus 3. Next, 3 1s 3, 4 1s 4. 3 minus 4, it's minus 1. Next, 4 1s 4, 3 1s 3. 4 minus 3, it's 1. Next, 3 1s are 3, 3 1s 3. 3 minus 3, it's 0. Right? Next, 3 1s are 3, 4 1s 4. 3 minus 4, it's minus 1 again. Next, 3 3 0. 4 minus 3, it's 1. So this is the adjoint of the matrix. Okay, we have already got the adjoint divided by determinant. So A inverse is equal to this adjoint whole divided by 1. Whole divided by 1 means this 1 is divided by with every element. So finally we will get as A inverse is equal to 7 minus 3 minus 3 minus 1 1 0 minus 1 0 1. Right? So this is the A inverse. This is the way how to calculate A inverse of the matrix by using the adjoint shortcut and the determinant shortcut. Hope you understand. Now let us see what the rank of a matrix says. Okay, rank of a matrix. A non-negative integer r is said to be the rank of a matrix A if, which is nothing but non-negative integer. Always remember, rank is nothing but a non-negative integer. Okay, so how can we say the rank for a matrix? See friends, if there exists at least one non-zero minor of order r. See friends, for every matrix there are minors. Right or not? Previously we have discussed how many total number of minors are there in a matrix, right? In the same way, if there exists at least one non-zero minor of order r, then this r is called the rank of the matrix. Necessary condition is second one. If at all R is a matrix which is of non-zero minor, R is a matrix with the non-zero minor's order is that rank, right? So all minors of order r plus 1, if they exist, are zeros. Right? So if at all the minor I am having is 2, the minors I am having 3, their determinants should be zeros. That is the case. Then only the rank is 2. If the rank is 2 means non-zero minor is existing and that determinant is equal to 2, that is nothing but which is the order of that non-zero minor, But when we calculate all the minors of 3 by 3 matrix, then definitely their determinant is going to be 0. That is what rank is. So rank is denoted by row A and the order of the non-zero matrix of minor of order R, and rank of the matrix A is nothing but order of the largest non-vanishing minor of A. This is the definition of rank. Okay, in order to say in this lengthy process, this is the necessary condition actually, and necessary condition, and this is the exact definition of matrix, the order of any largest vanishing minor of A. Rank of the matrix, what does it say? What exactly rank means? It is nothing but the number of linearly independent rows or columns. How many linearly independent rows are there? How many linearly independent columns are there? We can generally tell basing on the rank. If suppose if the rank is 2, then in that particular matrix there are 2 linearly independent rows or 2 linearly independent columns. Fine. So this is all about rank. Somewhat this definition might be confusing for you, these two statements, but don't worry friends, when we are solving the problems you will understand what exactly rank is. Okay. Now friends, let us see the important properties of rank of a matrix. Okay. See, first one. Rank of a null matrix is always equals to 0. Okay. Next, rank of a matrix is greater than or equal to 1 if only if rank is not equal to null matrix. See friends, listen carefully. If at all rank is a null matrix, definitely the rank is 0. If at all it is not a null matrix, definitely the rank will be greater than or equal to -1. That means if the rank of the matrix is greater than or equal to 1, then rank is nothing but definitely it is a non-zero matrix. For only a null matrix itself, rank will be 0. For any matrix, rank will be greater than or equal to 1. Rank can be 1 and more than 1, but for null matrix it is 0. Okay. Next one. Rank of a matrix which is in the form of m by n order, that is rectangular matrix, which is less than or equal to minimum of m comma n. This means, see friends, remember, for example, I have a matrix which is of order 5 by 3. The rank of this matrix is definitely less than or equal to 3. The rank of this matrix will be 3 or 2 or 1. If it is a null matrix, it is 0, right? No need to find out. But for this matrix, the less than minimum number is 3, right? So less than or equal to 3. Okay, remember in this way. Next formula, next property. Rank of a matrix is n if A is a non-singular matrix. That means if A is a non-singular matrix, non-singular in the sense determinant is not equal to 0. If the determinant of the matrix is not equal to 0, then rank is nothing but the order of the matrix. Okay. If the determinant is 0, that is singular. If the determinant is 0, singular, then the rank will be less than the order. Okay, if the determinant is 0, the order is 3, definitely it won't be 3 here in this case. 2 or 1 will be the matrix rank, right? Next one. Rank of the identity matrix is always equal to n, because rank of the identity matrix in the sense identity matrix is always non-singular, right? Because the determinant of identity matrix is 1. So identity matrix rank is nothing but its order. Fine. Next, rank of a matrix and rank of its transpose of the matrix both are same. If you find the rank of the matrix and if you find the transpose after doing the transpose of the matrix, both are same. Rank will be same. So you do the transpose operation. Fine. Next one. Rank of AB is less than or equal to minimum of rank A comma rank B individually. If rank AB in the sense it is a product, right? This is the pre factor and this is the post factor. So if you want to see, this is one very important relations. They might ask you in the questions directly this property. Rank of AB is less than or equal to minimum of rank A comma rank B. If suppose rank A is 5, rank A is 4, rank B is 4. Let us suppose rank AB will be less than or equal to 4, friends. The rank A is 5, right? Rank B is 4, right? So which is minimum? What is the minimum value? 4 is the minimum. So rank AB will be less than or equal to 4. That means either 4 or 3 or 2 or 1. In that case it is possible. Now, and it is greater than or equal to rank A plus rank B minus n. In the sense, and the rank of AB will be equal to rank A in the sense it is 5, right? Rank B is nothing but 4, right? If suppose this is of the order of 3, The obtained matrix order is 3 minus 3. 5 plus 4 is 9. 9 minus 3 is 6. So greater than or equal to 6, friends. In that way we used to calculate. Fine? Okay. Next. Rank of A plus B is less than or equal to rank A plus rank B. This is very important property, and rank of A minus B is greater than or equal to rank A minus rank B. If here it is less than or equal to, there plus comes. If it is greater than or equal to, we have to do the minus operation. For minus operation, greater than or equal to, plus operation, less than or equal to. Remember. Next, rank of AB minus I is less than or equal to rank of A minus I plus rank of B minus I. Okay, remember these properties. And rank of the diagonal matrix is number of non-zero diagonal elements. In the sense, I will give you a small example. If suppose this is the diagonal matrix, right? So these are zeros, these are zeros. So what is the rank of this matrix? This is the diagonal matrix. Number of non-zero diagonals is nothing but 2. So rank of this matrix is 2. If at all this is not equal to 3, once again there are 3 non-zero numbers in the diagonal, the rank will be equal to 3. So diagonal matrix rank is nothing but number of non-zero diagonal elements. So these are the important properties of the rank of a matrix. These are very important. Hope you understand, and please revise these properties of the rank of the matrix thoroughly so that you will remember it. Okay.